In this session, we will look into broadband antennas, another cluster of antenna designs that is covered in this course, BEE 4433 Antenna Theory and Propagation. Broadband antennas are typically large in size. An interesting characteristic of this antenna is that the pattern, gain, and impedance remain acceptable and are nearly constant over a wide frequency range. This type of antenna exhibits constant, low to moderate gain properties while having real input impedance and wide bandwidth. Throughout this session, we will look into two types of broadband antennas, namely helical antenna and log periodic dipole array antenna. A helical antenna is an antenna consisting of one or more conducting wires wound in the form of a helix. The wires can be in the form of monofilar, bifilar, or quadrifilar, with 1, 2, or 4 wires respectively. In principle, helical antenna radiate omnidirectional patterns. However, in most cases, helical antenna are mounted over a ground plane so that it could generate directional pattern. The feed line is connected between the bottom of the helix and the ground plane. Helical antenna can operate in one of two principal modes, normal mode or axial mode. Helical antenna generates circularly polarized radiation and is dependent to the direction of the wire curl. Let's look into the details of a single-turn helical antenna with diameter D and a ground structure. To achieve the desired directional radiation, the ground plane should at least be 3/4 of a lambda. This specific helical antenna has a pitch angle of an alpha degree, termed as pitch angle. The unrolled structure of the helical antenna is as shown in this figure. S is the vertical separation between turns for the helical antenna. The circumference of a turn is calculated by multiplying the diameter with pi. Total height of the helical antenna is estimated by multiplying the number of turns with the spacing. In general, helical antenna gain increases with the increasing number of turns, and impedance value of helical antenna relies on its pitch angle. Now, let's analyze the performance of a helical antenna that was simulated earlier. The antenna's reflection coefficient results confirm that the antenna is operating in a wide frequency range, approximately around 1.24 GHz, equivalent to 55%. The polar plot shows that the antenna has a directional radiation profile. The antenna has a circular polarized radiation at broadside, whereby the axial ratio at this range is less than 3 decibel, approximately around 107.5 degree. An example of helical antenna design is shown here. Near optimum circumference is calculated using this formula. Spacing for near optimum pitch angle design, input impedance, half power beamwidth and first null beamwidth, directivity, dimensionless and in decibel. Finally, the axial ratio. Next, let's have a look on the operational mechanism of another broadband antenna, the log periodic arrays. A log periodic array is a multi-element directional antenna designed to operate over a wide band frequency range. The log periodic array is frequency independent in that the electrical properties such as the mean resistance, characteristic impedance of the feed line, and driving point admittance vary periodically over the logarithm of the frequency. In the case of a log periodic array antenna shown here, the elements are a set of dipole antennas and are connected to the transmitter or receiver. The coaxial feed cable runs along the length of the lower metallic support boom, and the boom are connected via a balloon. The shortest dipole with L1 length contributes to the highest frequency of the array, while the longest dipole with L6 length contributes to the lowest frequency of the array. The more number of elements, the wider the bandwidth is covered by the antenna. The log periodic dipole array radiates in the direction of the feed and exhibit an end-fire radiation pattern. The boom length is L. The Rn is the position of the nth element. Ln is the length of the nth element. Alpha degree is the half apex angle. Dn is the diameter of the nth element. Sn is the gap spacing at the feed point of the nth element. When plotted against frequency in logarithmic value, the input impedance is periodic. Example, it repeats itself at a regular frequency interval, hence describing its name as a log periodic dipole array. In general, the design tips of an LPDA include the gain increases with the scale factor, and the input impedance is directly proportional to the boom spacing. Design parameters related to a log periodic dipole array includes diameter of element and feed lines, input impedance, while performance parameter of the antenna includes frequency response and directivity. Half apex angle is calculated using this equation, in which it is influenced by tau, the scale factor, and sigma, the relative spacing. Boom length is estimated based on the desired bandwidth. Number of elements depends on the desired bandwidth and the scale factor. The bandwidth of the antenna system is calculated using the following equation, whereby the active region is between the first and the last element. The input impedance of each element is influenced by its length and diameter. This graph shows that the directivity increases with the increment of the relative spacing. Similar trend is also observed for the scaling factor. To achieve the desired resonance, dipole length should be increased when the diameter of the conductor is increased. Let's look on the performance of a log periodic dipole array simulated earlier. The resulting graph of S11 over frequency affirms that the log periodic dipole array is operating at a very wide bandwidth, approximately around 1.6 GHz, equivalent to 67%. This is also shown through its VSWR response. The antenna exhibits directive radiation pattern with a half-power beamwidth response of 65.1 degree. The antenna is linearly polarized as the axial ratio response exceeds 3 decibel mark. Throughout this session, we had looked into broadband antennas, namely helical and log periodic dipole array. While the radiation pattern, gain and impedance remain acceptable and are nearly constant over a wide frequency range, the broadband antenna exhibit low to moderate gain. For wireless application that requires high signal strength, antennas with high gain are required. The high-gain antennas provide a more precise way of targeting radio signals and are therefore very essential to long-range wireless networks. They even amplify weak signals used in satellite communication. So, in the next coming session, we will look into high-gain aperture antenna design.